Hello, friends. I welcome you all for my lecture on scattering theory. This is my lecture number 5, and today we will extend the partial wave analysis. We have studied the partial wave analysis in the previous lecture 4, and you see we have used the Schrodinger equation, which is mentioned here. This is as equation number 1, which is already you know that del square psi plus 2 mu over h cross square E minus V of r psi is equal to 0, where mu is the reduced mass of a system of two particles, and here V of r is the potential. And you see our wave function psi is only a function which is depending upon theta and phi. It is independent of phi because your incident particle is moving along the z-axis. And since it is depending upon r and theta, we can split the radial part, the wave function into the two parts, the radial part as well as the angular part. So this equation 2 indicates that psi of r theta is a product of the radial part and the angular part. The radial part RL of r satisfies the radial wave equation which we have developed in a previous lecture, which you can see that 1 upon r square d by d of r square d by dr of r of L, and you have the square bracket term 2 mu e over h cross square minus 2 mu v over h cross square minus L into L plus 1 over r square, and this is your radial wave RL. And you know that n is orbital quantum number which takes discrete value, which is quantized, and which possible value is 0, 1, 2, 3, 4. And we wrote the solution of the radial wave equation when V of potential V of r is 0. So when a particle is very far from the scatterer, when it does not experience a potential, and when it does not experience a potential, then the V is equal to 0. So when you consider V is equal to 0, and when you solve the solution of equation number 3 in the case where a particle is very far, very large distance r, which we have considered, this distance r, when a particle is at a very large distance from the scatterer, when the particle is not in the region of potential, because you see you have a particle which is generally considered as a target, and this target is kept along the z-axis at the origin, and surrounding this target particle you have a region of potential. There is a range of potential. So you may imagine that surrounding the particle you have a sphere of radius r0, and if a particle or incident particle enters in this region of a sphere, that is in the range in the range of a potential, it will experience a potential. But if it is away from the range of the potential, it is very large. Let us say it is very large distance. We want to see the asymptotic solution for that. So it's asymptotic solution where V is equal to 0. In that case, the solution of equation number 3, the radial solution, is given by RL of KR, where K is the wave vector, because you consider that our incident particle, we consider the plane wave. The plane wave is considered e to the power of ikz, where that K is a wave vector. So RL of KR is given by A dash JL of KR minus B dash NL of KR, where A dash and B dash are the constant which is calculated when the potential V of R is equal to 0. You see, this solution, we have two special functions appearing. One is this is GL of KR is known to you. It is known as a spherical Besson function of order L with an argument KR, And when this R is very large, suppose if you consider Kr is equal to rho, so here I wrote the definition GL of rho. This is a spherical Bayesian function, please remember this is not a capital J. So GL of rho is equal to 1 upon rho sine of rho minus n pi by 2 when rho tends to infinite. And you have another special function which appears in the solution of the radial part is the NL of Kr. This is a Newman function. It is a spherical function, and it is order of L. It is given by minus 1 upon rho cosine of rho minus L pi by 2. You know the special features of this Newman function that if this rho tends to 0, that means this is the we are here. I wrote the definition of the Newman function of order L when rho is infinite, when rho tends to infinite at a very large distance. It is given by minus 1 upon rho, and you have a cosine function rho minus L pi by 2. But if rho tends to 0, that means if it is very close to the scatterer, I would say very close to the scatterer. If rho tends to 0, then the NL of rho is not a finite function, it's an infinite function. And I think I gave you this exercise to show that NL of rho is an infinite function. It is right, and when rho tends to infinite. So we discuss the solution of this when we have a Google meeting. We will discuss this. So you see this part here I can write analog KR because at large distance it is no it is not infinite. So it is basically given as minus 1 upon rho cos. So we have the solution of radial wave equation in the region where potential is zero, where is at the large distance. This is the solution. And now I can substitute the value of spherical Bessel function at a large distance, which is defined by this equation. And here also analog care, I can write down this. So you can see instead of your argument is kr, so you have to write down the value of the GL of kr. So it is a dash 1 upon kr. This is 1 upon rho is 1 upon kr. Sine instead of rho you have to put kr minus L pi by 2. And you see this is the minus sign. And the NL of rho at a very large distance rho, it is also a minus sign. So these two minus sign ultimately gives you a positive sign. B dash 1 upon kr cosine of kr minus L pi by 2. You see, this is the solution where you please remember that this constant a dash and b dash are the constant which we have been calculated in the case when v of r is equal to 0. Now our basic problem is that we want to study the solution of the radial Schrodinger equation. Of course, we want to see the asymptotic solution, but here we want to find out the solution when v is equal to not 0. I mean, sorry, when v is not equal to 0, you have some potential. So when a particle is experiencing the potential, when a particle is entering in the region of potential, when particle is entering in the range of potential, a particle experience a potential. When a particle experience a potential, then there is a process of scattering takes place. So your radial part, the phase of the radial part will be altered here. And here we want to write down the solution of the radial wave equation in presence of V of R. This is the equation number 4 is a solution of a radial wave equation in absence of the potential. But when you want to write down the solution of the radial wave equation in presence of potential while considering the solution number 4, we have to introduce some new constant, because you see when you want to write down the solution of equation number 3 in presence of potential, your solution by considering the solution in the region where v of r is equal to 0, you have to introduce the new constant. So here you see, let us discuss this matter very, very carefully. You see, when v of r is not equal to 0, right, then the value of constant a dash and b dash has to be determined, because you see this a dash and b dash is the value which we have defined when v of r is equal to 0. When you want to write the solution for the radial part in presence of the potential, this constant a dash will be altered, the constant b dash will be altered, and we have to define the new constant. So we are defining the two constant, and the two constant we are introducing. You see the two constant here. I'm introducing the two constant. I introduce a constant AL and another constant delta L, and these two constants are related with the constant a dash and b dash. You see, a dash and b dash are the constant calculated when the potential V of R is equal to 0, while AL and delta L are the constant that we are introducing in presence of the potential. So these new constants are related to the old constant via this relation. You see, A dash is equal to AL cosine of delta L. And now you have another equation, B dash equal to AL sine delta L. See, this delta L is a very important term which I will discuss. This is basically known as phase shift. So let me discuss what is a phase shift. You see, the radial part of the solution, you see the radial wave equation. When you see uh, when it does not experience a potential, then you have the equation number 4, that's a solution. But you see, when a particle is very close to the scatterer, when it enters in the region of potential, it experiences a potential, and when it experiences a potential, then the radial part, the phase of the radial part is altered. So the amount which is altered, that is, we want to see that how much part is altered is defined by the phase shift. So we want to understand the meaning of phase shift. So once again, I'm repeating that you can see here that this is the radial wave equation. You see, and when v is equal to 0, you calculate the solution. But when the potential v is not equal to 0, then the radial part will experience a phase, right? It will alter the phase, and that amount we will discuss with the help of phase shift. So please try to understand this equation which I introduce here. So the new constant which we have introduced here, a dash equal to AL cos delta L. So when there is no phase shift, when it does not alter the phase, you see, when it does not experience any change in phase, so you see a delta L is 0, then A dash is equal to AL. And you see, when delta L is equal to 0, so sine 0 is 0, so B dash will be equal to 0. So when you introduce the new constant, the constant AL and the constant delta L, and when I write the solution, the asymptotic solution in presence of the potential, I the a dash, the constant a dash is now altered, and I'm writing the new constant, that is AL. So I'm writing AL over KR. So it's 1 upon KR is remaining KR, and I'm writing sine KR minus L pi by 2, plus I'm writing the factor delta L, that is known as the phase shift, and we will discuss once again what is the phase shift here. So you see, this is the part, and you see the other part which is basically I have ignored, because you see, this is because of the Newman function. and 1 upon kr cosine of kr minus L pi by 2, you look at this. This is because of the Newman function which here, and you know that Newman function is infinite when rho is 0, that is a distance r, that the argument, you look at the argument which I mentioned here, rho, when rho tends to 0, NL of rho is infinite. And when a particle is in the region of potential, in the range of potential, when it experiences a potential distance r, that is the rho, here this distance r is very small, so your Newman function will diverge, it will diverge. So when you have a diverging wave function is not accepted, so when you want to write down the acceptable solution, in the case where potential is affecting on the particle, we have to ignore this part. We have to set b dash equal to 0 because the Newman function is infinite. So we allow only this part RL of kr equal to a dash, and instead of a dash we have to write down the new constant al. So we write down this constant al, and upon kr sine kr minus L pi by 2 plus delta L, and this I will give the physical interpretation of this delta L, which is known as the phase shift. And you see this is the phase shift. You see that this AL is the amplitude of the wave, and delta L, which I wrote it here, is the phase shift, measures the amount by which the phase of the radial function for angular quantum number L, right, differs from the corresponding case for p is equal to 0. So once again you see what is delta L. Delta L is the phase shift, measures the amount by which the phase of the radial function for angular quantum number L differs from the corresponding one for v equal to 0. Okay, so once again you see, I will explain. Look at this expression, which this is the expression number 3. We have the solution of expression number 3, which is written as equation number 4. This is the asymptotic solution which we have calculated, and you see that this radial part does not, when you solve this equation, when v of r is equal to 0, it does not experience any change in radial part. You see, it does not it does not experience any change in phase here. But you see, when this uh, particle experience a potential, it experience the potential, when it experiences a potential, so the phase of the radial part is altered. So there is a change in the phase of the radial part, and this change is considered as the phase shift. So I would say that this is something like the phase difference, I would say. So the phase of the radial part is altered because of the potential, and that part which is altered, how much part is altered, is characterized by the phase shift here, this delta L. So delta L is the phase shift. This phase shift we want to measure for various scattering, that is the scattering for S wave, P wave, V wave, we will measure the scattering also. So now once you understand the phase shift part, we will find out today the scattering amplitude. We want to find a scattering amplitude, we want to find out the phase shift, because you see, when particle experience the potential, the radial part is basically affecting because of the potential, the phase is altered, and there is that phase part, we want to find out the phase shift here. So that phase shift we will So now with this concept of the general solution, you see, once you get the radial part in the region of potential where particle experience a potential, because of the potential there is a existence of the phase shift. The radial part is affected because of the potential, and this is measured by the phase shift. So this expression is an RL of Kr, which is the solution which we obtain in presence of potential. And once you know RL of Kr, you substitute this RL of Kr in the expression of the potential which we have taken here. This is the wave function psi of r theta, and RL of r, which we have calculated the asymptotic solution of the radial wave equation, which we will substitute here, right? So when you substitute this part here, so you have the most general asymptotic solution of a Schrodinger wave equation is given by the expression of psi of r theta, because this is RL of Kr. You see RL of Kr, I'm keeping the value of RL of Kr here. So it is AL of Kr sine of Kr minus L pi by 2 plus delta L PL cos theta, where delta L is the phase shift which we will measure, right? And this phase shift will give you it will give the information regarding the scattering that we want to understand, and we will find out the scattering amplitude. We want to find out the probability of a scattering in a desired direction. Also, we will calculate. So these are the two factors which we will calculate. So now, once you know this equation number 5, and we have equation number 6, which we have already developed. You see, this is the equation. This is the asymptotic form of the wave function in terms of a scattering amplitude. You see, this is the scattering amplitude. F theta is the scattering amplitude, and you know this is e to the power of I k z, which is basically it is the plane wave expression, because we have a particle. This particle has two eigenstates. This eigenstate is basically indicating the plane wave. This is basically an incident particle moving along z direction, is represented by a plane wave. And this is a scattered particle, because when the particle is scattered, you have a spherically radial, you have your spherical wave which is moving radially outward direction. You see, so this is basically the scattered wave. This is the incident wave, and you have the most asymptotic form of the wave function which we have already developed in terms of a scattering amplitude f of theta. And so this, you know, e to the power of I k z is the plane wave expression, and this is e to the power of I k r, basically indicating radially scattered spherical wave which is moving in a radially outward direction from the scatterer. So this expression is known, and the most general asymptotic solution that we have developed, equation number 5. This is the equation number 5 which we have developed, the equation radial solution in presence of the potential which we have calculated. We have a constant AL, and constant AL is related with constant A dash, is A dash equal to AL cos delta L. And you please remember, when there is no phase shift, A dash equal to AL, and you see delta L equal to 0, so sine 0 is 0, so B dash is equal to 0, and you will have the most general solution which you can write by RL of Kr with this expression. So I have these two expression, expression number 6 and expression number 5, and you see the left hand side is psi of r theta, here also psi of r theta. So I can compare these two equations. So let us compare the right hand side of equation number 6 with the right hand side of equation number 5, because both are the asymptotic solution. This is also asymptotic form, and this is also the asymptotic form. So let us compare these two part, you have the comparison of right hand side of equation number 5. So you see the right hand side of equation number 5. Equation number 5 is e to the power of I k z, right? So I write plus f theta e to the power of I k r over r. So this is also I wrote it here. And right hand side of equation number 5, so right hand side of equation number 5 is mentioned. Now please concentrate, this e to the power of I k z is a plane wave, and you see that the plane wave can be regarded as a linear combination of infinite number of spherical waves. And we have developed the Boyer's expansion, and you see in previous class I have developed the Boyer's expansion, that e to the power of I k z is basically a linear combination of many spherical wave, right? The linear so and each individual wave is considered as a partial wave. So you have the wave corresponding to L equal to 0 is known as S wave. Your wave corresponding to L equal to 1 is a P wave. So you have basically a linear combination of many spherical wave, and each spherical wave is treated as a partial wave, and we are basically taking the analysis of the partial wave, and that's why this is analysis of the partial wave analysis. And we have developed this e to the power of I k z is equal to sum over L, where L changes from 0 to infinite. We have I to the power of L at 2L plus 1 GL of KR PL cos theta. This is we have developed, this is known as the Boyer's expansion. So I substitute the Boyer's expansion here. So you see the left hand side of this equation, I substitute e to the power of I k z. So you see this is I'm writing L equal to 0 to infinite I to the power of L 2L plus 1 JL of KR PL cos theta. This you can see here, and this the term remain as it is f of theta, because the scattering amplitude I'm writing e to the power of IKR over R, and you see this term sine AL over KR is remaining as it is, and you have a PL of cos theta. So this equation, I only make a change here. I substitute e to the power of IKZ. And now you see I have this special function. This is the spherical Bessel function of order L, and the argument is KR, and we are writing this expression for an asymptotic solution. So when KR, so R is very large, so you have a KR is very large. So when this KR is rho, when rho is very large, rho tends to infinite, I can write down is equal to 1 upon rho sine rho of minus L pi by 2. This you know, this is the expression you see here. JL of KR is 1 upon KR sine KR minus L pi by 2. This is the definition when R tends to infinite. So I write this expression here. So you see I to the power of L remain as it is over 2L plus 1, 2L plus 1. And JL of KR I am writing 1 upon KR sine KR minus L pi by 2. This is PL cos theta, so PL cos theta. So the first term, you can see I simply put the value of JL of KR when KR is very large, and you have the same factor, and you look at this term, the right hand side term, it is AL over KR sine KR minus L pi by 2 plus delta L. This is the phase shift part, PL cos theta. So this equation is known to you. Now, what we will do, we will put the value of sine kr minus L pi by 2, because we know sine theta is given by e to the power of plus I theta minus e to the power of minus I theta divided by 2I. This expression is known to you in a trigonometry. So look at this. This is I to the power of L. You can see, so 2L plus 1 and 1 upon KR. So I can write 2L plus 1, 1 upon KR as it is. And this is sine theta. So sine theta is e to the power of I theta minus e to the power of minus I theta divided by 2I. Theta is nothing but KR minus L pi by 2. So e to the power of I theta, so theta is this, e to the power of minus I theta, theta is this, divided by 2I. So I put this value, right, and this is PL cos theta as it is, f theta, you see f theta as it is e to the power of I kr by r, and that comes as it is. You see this is okay. And now you see the right hand side. Right hand side of this equation, you see I am keeping al over kr. So al over kr is that. Al is the amplitude that you know. And now this sine theta. So e to the power of I theta, theta is kr minus l pi by 2. So this minus e to the power of minus I theta. So theta is this kr minus l. So I am keeping this divided by 2i pl cos theta. So this equation is. And now you see we will have to simplify this equation. So we have to open the curly bracket term, dear friends. We have to open the curly bracket term. So when you open the curly bracket term, so first I will take the first term of the curly bracket with this with the term which is given here. So you can see here. So I take the first term, this I to the power of L 2L plus 1 kr with the first term of the curly bracket. So you see I to the power of L 2L plus 1 over kr. So it is mentioned here. Okay. And you see this term I can split into the two part, e to the power of I kr. So it is e to the power of I kr and into e to the power of minus IL pi by 2, e to the power of minus IL pi by 2, and this 1 upon 2i, so it's 1 upon 2i, and it is multiplied by pl cos theta, so it's pl cos theta. So first term of the curly bracket is multiplied here. Now you have to multiply this term with the second term of the curly bracket. So you see there is a sum over, so it is sum over. You see I to the power of L upon k, 2i is here, and so this 2i and k is here, and 12 plus 1, and the term is, you see the this will give you e to the power of minus I kr. So you see this is e to the power of minus I kr, right? And you see this is a minus and minus gives you plus, so e to the power of IL pi by 2. So e to the power of IL pi by 2 PL cos theta. So I hope you understand this term, right? And then you have f theta over r. F theta over r is just 2 I kr. I'm keeping this term as it is. So you can see the left hand side is simplified. Now look at the right hand side. Right hand side again you have a curly bracket. So you have to open the curly bracket. So you take the first term of the curly bracket, second term of the curly bracket. So now you see here once again, I write, I have mentioned each term. So this is AL over KR, so AL over KR, 1 upon 2i, 1 upon 2i, and the first term of the curly bracket. This gives you e to the power of IKR, so e to the power of IKR, and you see e to the power of I into bracket minus L pi by 2 plus delta. So this is mentioned, and the PL cos theta. So this is PL cos. Then there is a minus sign. So this is minus sign. So I'm going to put a minus sign. So you see this is AL over KR. So this is AL over KR, 1 upon TI. And you see this term, e to the power of minus IKR, e to the power of minus IKR. Please ignore this part. Into e to the power of minus I, you see, and into bracket it will be minus L pi by 2 plus delta L PL cos theta. So you see these derivation parts are very important, and you have to derive by yourself. You have to write each step very carefully. So what I will do, you see, I will upload the lecture note of lecture number 5 and lecture number 6 also today. Friends, in fact, I will upload all the lecture notes starting from lecture number 1 uh, to lecture number 5, and also lecture number 6 also I will also upload today. So all the lecture notes I will upload, and I request you to download all notes of the lectures, and you start reading the notes and prepare your own notes. And you see the next week I will arrange a Google meeting, and I will take your questions. Your questions are welcome. And during that Google Meet, you can ask me your questions, your doubts. We will discuss it, and I will solve all your problems related to the scattering theory. Well, friends, I will stop here. Next lecture, we will proceed further with this same equation. and we will calculate the scattering amplitude that we want to find out, and we want to also find out the phase shift also. So next lecture we will calculate it. So I'll stop here. Thank you very much for listening. Thank you.